My name is Pedro. I'm a new, very recent assistant professor, as Isabel said, here at Technical, but I developed my work in the last 4 years at Ghent University. So today what I will be talking about was developed at Ghent University. Also because most of you know me from here as well. I also did my PhD here, so I don't think it's very interesting to repeat again what I did in my PhD. There will be a snapshot at the end, but today we'll mainly focus on the work I developed at Ghent. So the title is From Catalyst to Process. What does that actually mean? We can start at a very micro level or micro scale in the bottom of the figure, and you'll have the mechanism. So there, it's how it happens at the molecular level. The scale above, you have the catalyst, which catalyzes the reaction, and you can control at the lab scale. Further, the kinetics gives you a macro perspective of what's happening in your reaction mechanism and the action of your catalyst, catalyzing that reaction. But you can go above to the reactor in the process and to the process itself. So the idea here is that instead of just working at one of these scales, which we all do, and it's surely very important to get more in-depth understanding of each one of these scales, but the idea here is to integrate a few of these scales to learn how to reach the process level and to better control the process level. So during this presentation, I will be taking a few of these levels and discuss the work we did around those levels. The first part is about kinetic models and how to get kinetic models from open data. So the fourth part I would like to discuss with you is why data and why open data. So what we typically do is to go to our labs, acquire data from our experiments, and use it in a first loop to extract some information, some correlations or some qualitative information about our experiment. And in the second loop, the second step arrives to knowledge, which we communicate to our peers via papers. Now, this is not very nice, and we must do that, but it means that most of the times data is as a single use. And after getting a paper out of it, this data goes to the waste bin because we don't make it available such that others can use. So why do I care about open data? To make sure that we have some data circularity. So that means that we can have recycling the data back and reuse it for further information extraction and knowledge divulgation, creating large databases of open scientific data. Now, the question is, which data can we use, or what can we do with our data in Catalysis? There's what we call the Catalysis informatics toolbox. So we do have data, and we do want to reach at the knowledge about our catalytic process. What can we do? We can, first of all, apply some methods that can give us information about our data. So these are the typical data science, the statistical methods. So regression methods, simplified mathematical models, and some other more common machine learning methods as dimension reduction and classification methods. But what we really want to achieve is knowledge, because all that is only correlation. So it does not prove a cause-effect relationship. How can we reach knowledge about a catalyst, about a reaction mechanism via a microkinetic model? This microkinetic model, as a description, includes a reaction mechanism and has a detailed description of the reaction rates at the level of the active site. We'll go a bit through this again, but this is the main point. We want this data to arrive to a knowledge about our system, which is, in this case, a catalytic system. So get back a bit just to the basics. What is really a kinetic model? Because for me, when I arrived to Ghent, it took me a few months to understand what really people meant with a kinetic model. So we start with a very basic global reaction. With this, we can write what we call the net rates of formation. So for each individual component, we know in every reaction, the component is involved, and we can relate it with the reaction rate. So with that, we can calculate the net rate of formation of every single component. Then we need for every reaction, and not anymore for every component, we need a reaction rate, and this will depend, of course, on the reaction network and the mechanism that we consider. So here we can have plenty of changes. We can play with this as well. We'll arrive to something of this shape with a description of a reaction rate and elementary chemical steps. And then we need a description of what is the place where the reaction is taking place. So the reactor, and here we do a mass balance to each species inside in this, depending on the type of reactor we are considering. In the lab, we try to simplify and, of course, work with ideal reactors. If existing, we should also account for transport phenomena in this kinetic model. In the lab, again, we'll try to avoid them to simplify our model. What we care is kinetics and mechanism, and not transport phenomena when we are designing a catalyst or getting a kinetic model. So we went through kinetic models. Now, which data can we use for kinetic modeling? Typically, we go to the lab, we acquire data in such a fixed bed system for heterogeneous catalysts. There's inlet flow rate, we control the pressure, the temperature, and of course, we also control the outlet and measure the composition, typically via gas chromatography. What do we get in the format of data? There's a bunch of independent variables. So the data about the catalyst, the operating data, and the reactor data. This is our inputs to our system. And there's the dependent variables. So what is the result of our manipulations in the lab? And here we'll have the direct information from the GC is the outlet stream analytics. So some compositions. What we do next is to get flow rates, because it's typically a flow system. So you calculate flow rates. And most likely what we share with our colleagues are performance indicators, activities, yields, conversions, and so on. This is the point is coming. I guess this sounds super basic, and it is. The point is, when sharing the data, we should share the most basic information, or the one that comes immediately from our lab setup. So this is what is called a fair practice. So the best practice to share data is to share the outlet stream analytics. That means that our colleagues, our peers, can do their own assumptions, their own calibration factors, and check the material balance as well themselves if we provide the outlet stream analytics. So this is to tell how can we better share data, and then how to foster the use of open data. So now that we know where we want to get the kinetic model, we know which kind of data we'll have. The question is how to go from one to the other in a smart manner. So first, we need to just look a bit better at our data. So if you think about kinetic data, as I was kind of describing, you have operating data on the one hand, which is your independent variables, then the outlet flow rates on the other hand. You go to the lab, we change some operating conditions, temperatures, pressures, eventually catalysts. How much data does this come to? A few tens of points, max a few hundreds of points. The point here is that when we work with data, when we apply data science, we are talking about very big data. So the scale is completely different. In kinetic catalytic data, we have a few kilobytes. If we group data from all over the world on a single reaction, let's say CO2 conversion, we might have some megabytes, but this is very different from what is typically big data, which is on the order of terabytes per day, or even other types of techniques like SAS that can generate also a huge amount of data. So when we want to explore kinetic data with data science methods, we need to be very careful, or more, I think more importantly, we need to adapt these data science methods to the size of our data. So I'll put it in another way. The power of data usually is size. That's not the case for kinetic data. The power in kinetic data is the information. We need to cope with the small size. How can we do this? So what we would like to get from small data are nice trends. I think we all have the experience. If you try to do a graph, automatic graph in, let's say, Excel, you very rarely will get to a very nice trend like here, right? It's basically impossible. So our task here was to get to such a nice trend, such that we have a mathematical description of our trend, which we can afterwards use to build a kinetic model upon. So this was our challenge. What did we do? So we generated a tool which was based on two main parts. And now here I'm focusing on this feature extraction box. So there was a smooth curve generation, which is the Excel algorithm, which we improved for this type of data. And then there's what we call a primitive recognition. So this is what recognizes the shapes. So here you see G on the one hand and C on the other hand. These are two different types of primitives. The first and the second derivative are different. And with that, we can identify what are the trends, if this is a smooth increased trend, if there's an inflection point, or which kind of trends we do have. So what we did here, I will not go into the details because I think it will be too detailed and a bit boring for the sake of this presentation. What we did here was to take the typical data science algorithms and reduce the scope of these ones with knowledge of kinetics. For instance, we know that these kind of smooth trends are typical in kinetics, but if you see many variations like a sinusoidal trend, this is not typical of a pattern, for instance, of selectivity versus conversion. These trends are typically smooth. So this was the kind of knowledge we incorporated there. What could we do with this? At the moment we had the trends. From our data, we can just compare them with the trends from our models. So in the right part of the scheme, in the blue part, we have a database with rate equations. So they can generate any rate equation possible in Catalysis, within certain assumptions, obviously, but any possible rate equation for a given reaction. And we simulate the curve. And via a comparison algorithm that we also made, we can run rate equations and determine automatically what are the possible rate equations for a certain system. So to summarize, we start only with data. We analyze this data automatically via the algorithm, and the algorithm, based on the database of rate equations, will determine what are the most likely rate equations. This is very important for people working with kinetic modeling, because this process usually takes months to years to determine, to compare models and determine which ones are the most suited for our data. We verified this with a very old data set that has been around for ethanol dehydrogenation. You can see here on the right part is the results of the different models and the comparison with experimental data. And you'll see that only this model E really fits the experimental data. And indeed, this corresponds to the primitives that were determined, the first increasing trend and then a decreasing one. So this was the first part, was getting from data to a kinetic model in an automated manner via data science. The second part is about catalyst design. What does this mean? We want to really know how to design our catalyst from fundamentals, from kinetic models, from this information we just got in the first part. So what is the catalyst design problem? It's what we call an inverse design problem, right? So we know where we want to get, selectivity, activity, and stability. The problem is, what should we do in the lab in terms of, for instance, composition, support, size of the metal particles? So we have a huge design space, things we can play with in the lab, parameters, and a target performance. What is the challenge? Not only the size, but the many dimensions. So there's a lot of parameters we can play with in the lab. And this relationship is highly complex and nonlinear. So there's no straightforward relationship between a catalyst performance and the synthesis parameters in the lab. So how can we go stepwise? So what the kinetic model does is to link some descriptors of the catalyst to the performance here in green. Now, what we really want to get is to the synthesis parameters or to the properties of the catalyst. So what we need is basically to make a link between these properties, the descriptors, and the performance. How did we approach this? First, we know that with the kinetic model, we can go from descriptors to performance. We have this correlation. That's what the kinetic model is about. In experimental catalysts, you have the properties you synthesize in the lab, plus the performance. The question is how to match then the descriptor and the properties. To do so, we had a combined approach. So we again used kinetics, but also we used statistics because we are missing this relationship between properties and descriptors. So giving a case study for oxidative coupling of methane. These are, in the left side, you have the catalysts that have been tested throughout the years. So there's quite some experimental catalysts, and we know the composition that is around. How to get the descriptors? First step, we did plenty of simulations playing with the kinetic parameters virtually, and we started filling in all the performance space here. So what you see in round circles are all the simulated catalysts. So now we get performance of experimental catalysts and performance of simulated catalysts overlapping. How to really tell that a real catalyst is similar to a virtual catalyst? We need some criteria. So for that, we use statistical analysis, the so-called clustering method. And what you see in colors here are groups that are statistically similar. So for instance, if you take yellow, all the round circles which are simulated catalysts are statistically similar to the 3 experimental ones that are, for instance, zirconia and niobium based. So we start getting some information about the relation between performance and properties or composition. Now we want to really go to the descriptor level because that's what we can simulate in our model. So the kinetic parameter level. How can we do that? We start analyzing we analyze the differences between the groups. So if you take the yellow and the green, you can compare the descriptors of the yellow that were simulated with the descriptors of the green that were simulated. If you look more into detail into a selection of descriptors, what you can see is that, for instance, the yellow ones had a much higher reaction enthalpy to abstract hydrogen from methane than the green ones, which means that this can be also correlated with what we observed in the lab. In the lab, we know that these yellow catalysts, so the niobium and the zirconia ones, are weaker in terms of basic sites as compared to the green ones, which are from lanthanum, for instance. So in the x-axis, we do have what we observed in the lab. In the y-axis, we have the simulated values, and we can then compare the differences. And it's clear that when you go from a weak basic catalyst to a strongly basic catalyst, we can increase the performance from low methane conversion to a higher methane conversion. So this is a depiction of what we can do and how can we get the relationship between a descriptor, a performance, and the properties in the lab. So now we know if you want to get a certain performance, which basicity you should aim at. To summarize these first 2 parts, there are 2 types of data sets in catalysis and different things we can do with that. The first type are very small ones. We can do automatic trend recognition with the tool we developed and know what's happening in that trend and have a digital information about it. Secondly, based on that digital fingerprint, we can get automatically also a kinetic model. For larger data sets, which come from various labs around the world, we can do data comparison. So we can analyze the different results and the differences within them. And more importantly, you can do a mechanistic interpretation of this result if you have a kinetic model. Based on the kinetic model, you can do comparisons of groups of catalysts that we have identified. The third part goes more into the multi-scale simulations. So why we care about multi-scale modeling? What we all do, or what we have been doing, and it's normal, we do it to develop catalysts on the one hand, on the other hand, develop reactors, and on the third hand, if I could say, develop processes. So typically we develop all these three scales individually. And then we look for an industrially viable implementation. Now, again, in the same example of oxidative coupling of methane, there's all this bunch of catalysts that has been developed. Have this been integrated with the process? No. Usually we test one catalyst when we do process simulations, or we evaluate one catalyst kinetics when doing process simulations. Then for reactors, it's the same story, right? So there's very nice reactor designs, fluidized beds, or in this case, bubbling beds and fluidized beds, for instance, but we cannot use this in process simulation, or we don't use for the sake of easiness, we don't use them in process simulation. So what we would like to do, and that's the multi-scale aspect of it, is to integrate the scale of the catalyst, the scale of the reactor within the process scale, to have a process that is adapted, tuned to the reactor and to the catalyst. We have all this information in the process simulations. So how we did it in practice, so this is basically a manual guide. You can do it at home. The practical part is not too difficult to start with. We worked with Aspen Plus, which is a common simulation software, and we define the user block, which is our reactor. So in this user block, what you need to give in and out. So in, you'll get the information from Aspen, the stream before or at the inlet, and out, you need to give information to the Aspen of what happened inside this dummy block. The important part is what do you do with this block, which is supposed to be your detailed reactor. So here, we used heterogeneous fixed bed reactor model, which accounts for the transport phenomena inside the catalyst particle, and has implemented a microkinetic model, so with the detailed active sites, with a radical arc and the surface mechanism of the OCM reaction. So within this reactor block, all the complexity that is relevant of the reactor and the catalyst is included and will have an influence on the process output. For instance, the most simple one case study we did, it's a multi-stage reactor. So with one catalyst, sodium manganese tungsten, we simulated one stage and a two-stage reactor. You can immediately see that the selectivity would drop in blue, but yield would slightly increase. Now, this is a result for one catalyst, and just to prove my early point, I will show you a second catalyst. This is a strontium lanthanum catalyst. In this case, if you have one stage, the selectivity is low, but if you add the second stage, the selectivity will definitely improve, and the yield will even increase 3 times. This is to make the point that indeed accounting for the catalyst in process simulation is very important. The outcome can be quite different, and with this methodology, with the multi-scale methodology in process simulation, we can arrive there. We can also use, of course, for a larger process, and here we are comparing the difference between just the reactor, which is the result we typically get from a kinetic model, to the whole process. And here also we can see quite some differences. If you, for instance, you take the local, so the outlet of the reactor, yeah, the selectivity is barely influenced when you do a recycle, and the yield decreases only slightly. Now, if you take the whole process, and this is maybe not too unexpected, and you close the loop, so if you recycle most of your methane, you'll get a huge increase in the yield up to 60%. So this is to give the other side of the story. If we also only do reactor simulations, we are also not seeing the whole the whole, not getting the whole picture. So to summarize, I didn't want to take too long, so I hope I'm up to time. In the first part, we were discussing how to get from data to reaction kinetics. For this, we used open data and data science. The bottom line being, we can extract knowledge from data if we have if we adapt data science tools. The second part, we went into catalyst design, and the message here is if you have a good microkinetic model, and again, you combine it with the right tools from data science, we can get to a very nice synthesis descriptor performance relationship, which will guide us in the lab instead of going based only on intuition. Last part, we integrated the catalysts and the reactor. So we integrated all the scales at the process level. And this made a huge difference, or was important to the outcome of the process. And that made a difference in the kind of decisions we take during design and synthesis of processes. So this was the scientific part of my presentation. I will now take a few minutes to go to do the more personal part and introduce a bit myself for people that will not know me before. So I was born in '89. I'll be very young for some people and old for others. So that's I'm somewhere in the middle, I would say. I did my bachelor and master degree here in Technical. I had my first research experience in 2008. So my first experience also in CPE with Fernanda Carvalho and Margarida Salema, and I started with homogeneous catalysis. I moved to heterogeneous catalysis for my master thesis, which I did in IFP EN in France, and it was a project also in collaboration with Michelin for renewable tires, so it was quite interesting. Then I did my PhD, so today I didn't talk about my PhD much, so I will now take 30 seconds to talk about it. My PhD was also a collaboration between Technical and IFP EN, and was supervised by Filipe here in the room, João Silva from ISEL, and two colleagues from IFP, Christophe and Antoine. And what was really the goal of my PhD was to make a bridge between what we typically study in the lab in hydrocracking, so very simplified catalysts, as zeolite support with some simple platinum particles on top of it, and a single model molecule as a reactant. And the industrial reality, which is a few molecules, also poisons. Here you can see sulfur and also, or hydrogen sulfide and also ammonia, which are typically poisons. We also have alumina, which is an industrial binder for these catalysts. So you can also have a catalytic activity. And the active phase, it's not platinum, but molybdenum, nickel, which is also sulfided. So it's a whole another complexity. And the goal of my PhD was to make a bridge between these two realities. And I think we learned quite some nice things about it. And in 2017, when I concluded my PhD, I moved to Ghent. Why exactly? For the kinetics and multi-scale part. I did a tiny bit of kinetics in my PhD after a lot of pushing from my supervisors, and I didn't know the power of kinetics. So I moved there to know a bit more about multi-scale modeling. And along the way, I also, with 3 other guys, we also founded the Young European Catalysis Network, something that did not exist in Europe for young people working in catalysis, and we have been making some nice events. And I hope getting young people together in catalysis. Just to tell a bit more about Ghent, I guess you might be curious. So I was there at the laboratory for chemical technology. So they are about 100 people now. You can see in the numbers, the main difference is to technical. So you can see that there's 12 professors for about 60 PhD students. That makes a difference. But there's also another, or as important one. Yes, that was my second point. There's 10 technicians for 60 PhD students. Now, I also must say that most of these technicians are not hired by the basic funding of the lab. It's all the competitive funding that pays these technicians. So they are not there granted forever. So it's a nice group, and the work goes, as you can expect from my presentation, from molecule to process. So we insist a lot on getting data at the laboratory level in combination with ab initio calculations. So calculations by themselves are not enough. Data by itself, it's also not enough. We need both, and this is the approach at the lab. Then we always get into a detailed kinetic mechanism or kinetic description of the mechanism. Then there's also people working a lot at the transport phenomena level. So there's a CFD group within the lab to achieve the so-called process and product design. So it's really from molecule to process. There's some 6 or 7 research groups that cover all these scales. Now I'll finish with the acknowledgements of the people that work in this work, because as you might expect by this point, I didn't do any of this by myself or alone. So there's a huge team behind. So Joris is the group leader, and Guimarães was the lab director when I was hired, and now is retired. Then there's Sebastian and Vasco, which were master students under my supervision, which worked on the part of the automation of the kinetic model construction. There's Laura, which developed, which was a PhD student, which I coached, and she developed the part on process reactor integration. And then there's Alexander, which is about to finish her PhD, but I didn't present any of the work today. And then there's Neboisha, Miley, and Yongang, which are my current 3 PhD students, still at Ghent University, and will conclude in the next few years their PhD. And then there's a bunch more of other people I would thank, which did not directly participate in this work, but which I contact during many projects there. Some more industrial, some more fundamental. And there's also the funding, I should acknowledge, particularly to the ERC funding and to the POF, which is the direct funding from Ghent University. And I would like to thank you for your kind attention.